Hello, statistics class. In this video, I'm going to go over Chapter 4, Section 5, Bayes' rule, which is actually a very important rule in statistics in general. But before we do that, we're going to do the law of total probability. So, the law of total probability is a property in statistics that allows you to rewrite an event into a more complicated. It takes this event and you can rewrite it more complicatedly. That's a word. Why would you do that? Well, you'll see, but I mean, I'm going to show you how to go from event A to this mess, but often we'll have the mess and we want to go to event A. But just what I would hope is that you understand how A is equal to what we're going to change it to. So let me just start at the top here. If we're dealing with colored blindness, and we have two sets of kind of people, men and women, a person who is a man is going to be put into set B. By definition, the complement of B would be everybody not a man, which would mean you're a woman. Okay, so what's important here, there's two things that's important about B and B complement. And these things are natural for complement, but this is going to be true for any time we're dealing with the law of total probability, that B and B complement must be mutually exclusive, which, since the complement of B is everything not in B, then it's going to be by definition mutually exclusive. But if we're given two sets that aren't necessarily complements of each other, then just in general, the two sets that we're looking at must be mutually exclusive. The other thing is that both or all, however many there are, because it doesn't necessarily have to be two, all of these sets must take up the entire sample space. So by definition, the complement of B is everything not in B, so everything in B and everything not in B will be the entire sample space. So we're going to say that we have a set A, okay? So we're going to have the set A is the event that a person is colorblind, right? I'm just reading this here. Since colorblind people can be either male or female, event A, which is a person that is colorblind, consists of both people. So while we know it's unlikely, or it's not unlikely, it's less likely for women to be colorblind. It's true that some women are colorblind. So event A, that a person is colorblind, can be either male or female, okay? So this is what might be a little bit tricky to explain, but let me try here. So it's possible to have the event that somebody's colorblind, A, and that they're a male, B. So that would be the event A and B. That would be the intersection of A and B. They're both male and colorblind, okay? A and B complement would be the intersection of colorblind and female. Okay, so all of A is split into two parts, male and female. Okay, so and A, the intersection of A and B is male and colorblind, okay? Actually, male and colorblind. And the intersection of A and B complement is female and colorblind. So all of the people that are colorblind would be the union of the males that are colorblind and the females that are colorblind. So what I was trying to say earlier, making A more complicated, is this. You can rewrite A as A intersection B union A intersection B complement, where B and B complement are mutually exclusive. Okay, that's important. There's no overlap. And B and B complement contain the entire sample space. Okay, B and B complement must be the entire sample space and must be mutually exclusive. No overlap. Then, if that is true, then the probability of A will be equal to the probability of the intersection of A and B plus the probability of the intersection of A and B complement. Now remember, this is the sum property, what we learned a few sections ago, the addition property. When there's a union, you can end, it's mutually exclusive, we know that these are mutually exclusive, we can add the two parts. Now, if they weren't mutually exclusive, we'd have the minus the intersection, but that's 0 in this case because there's nothing in common here. Okay? And so you might wonder, why would we do this? We're taking something that's simple and making it more complicated. Well, what's going to happen is we're going to more often have this side of the equation on the right, and knowing this information, we can then find probability of A. That's what if we knew what probability of A is, we wouldn't go make it more complicated. What's going to happen is we're going to be able to find the probability of A intersection B and the probability of A intersection B complement, and with that information we'll be able to find probability of A. Now, I hinted at this, I said this already, I think, that it doesn't just have to be two, there's not necessarily just two of these, it can be any number of sets that all make up the sample space. So the B part, the B and B complement part of this. So it can be 3 or 4 or 5 or 10, as long as all 10, if it was 10, are first mutually exclusive, and secondly that all 10 of them together make the entire sample space. Okay, so here's an example of 3, I think. Yeah. So here's an image. So this is a little more general now, and we'll get down to what's below that image in a second. So what we have here in a general picture, okay, now we're not dealing with colorblind anymore. This is something else, but in our colorblind example, this would be the people that are colorblind, okay? Okay, so but in this case, it's something different. So this is our set A, okay? Sample space is the entire box, anything that's possible at all, okay, in the entire scenario, whatever the scenario is. A is part of the sample space. The sample space is then divided into 3 sections in this example, but it could be any number of sections. And as you can see, when you cut the sample space, it's actually cutting the event A apart also, okay? So what we have here is the sample space S1, S2, S3. S is for sample space, but they're subsets of the entire sample space. And S1, S2, and S3, first of all, you'll notice that they're mutually exclusive because this line cuts it cleanly. There's no overlap between S1 and S2. There's no overlap between S2 and S3. Also, there's no overlap between S1 and S3. So mutually exclusive. Also, in addition to that, S1, S2, and S3, which, by the way, S1 is all of this stuff separated by the blue line, this stuff in here and this stuff outside. So S1, S2, all of this, and S3 all together make up the entire sample space. So we have A in here, and A is part of A is in S1, and it's cut. So there's a section right here. Ooh, section right here, which actually I could try and draw this with my pen. This might be a little ugly. So there's a section right here. Okay. This section right here is A intersect S1, which S1 is the entire thing. Okay. There's a section right here, which is A intersects section 2. And there's a section over here, which is A intersects section 3. Okay. So, sorry. So A, let me regain my thoughts here. A will be, the entirety of A would be the union of this section, this section, and this section. So it's a union of these three intersections would make up A. Okay, and that's what this is saying up here, right here. And then you can separate. You can change that so that P of A is the sum of those intersections. So whatever the probability of this is, plus the probability of this, plus the probability of this will be the probability of all of A. Hopefully that is making sense. Okay, so we need to do something else though, because we have these unions. We're actually going to take that one step further using the multiplication rule. So we have probability of A is equal to the probability of the intersection of A the probability of, let me start over. Probability of A is equal to the probability of the intersection of A and S1 plus the intersection of A and S2 plus the intersection of A and S3. Okay, now if we knew the intersections, that would be great. But let's say we don't know those, okay? Well, we're going to take these intersections. We don't know what the probability of these intersections are. We're going to use the multiplication rule that we learned in a previous section. So the probability of A intersection S, say 1, will be equal to the probability of S1 times the probability of A given S1. Okay? So this is actually what the law of total probability is. We're going to take that intersection. We take the unions and make them pluses. We take the intersections and make them multiplication of this form. Okay? That the probability of A will be equal to the probability of S sub 1 times the probability of A given S sub 1 plus, in this case, the probability of S sub 2 times the probability of A given S sub 2, and only in this case, this is a generic one that goes on for S sub k, because if it's in 10 parts, then you'd have 10 of these. If it's in 5 parts, you'd have 5 of these. In this case, we would have 3, so there'd be one more. Probability of S sub 3 times the probability of A given S sub 3. Excuse me. And that is the law of total probability. Okay? Are you ready for an example? Example 24. Sneakers are no longer for the young. Oh, so most Americans wear sneakers. Own sneakers. The table below gives us the fraction of U.S. Adults 20 years of age or older who own 5 or more pairs of sneakers. Okay, so the fraction of U.S. or the fraction of people with 5 or more sneakers. Okay, and then they have ages here. But then you'll notice that it also gives us the fraction of U.S. adults that are older, 20 or older. Okay, so the bottom one is the percent of people in the U.S. that are older than 20. So 9% of people older than 20. Okay, the top one is the percent of people, or the fraction of people, that own 5 or more sneakers for that age range. Okay, so we have to keep that in mind. And they want us to determine the unconditional probability of an adult 20 years or older owning 5 or more pairs of sneakers. So they want to know, what is the chance that anybody over 20 wears 5 or more, or owns 5 or more pairs of sneakers. Okay. So, the thing about this is that you have to consider is, so we're looking at people between 20 and 24 that own 5 or more pairs of sneakers. 26% of people between 26% of people between 20 and 24, the age 20 and 24, that own 5 or more pairs of sneakers. But the age range 20 to 24 is 9% of the total population, okay? And that's the important part, that this percentage is based upon this age range, okay? So if we wanted to find, and this is where this comes into play, if we wanted to find what percentage of people, all people, okay, not just the percentage of people between 20 and 24, but what percentage of all people between the age 20 and 20, or sorry, what percentage of all people are between 20 and 24 and own 5 or more sneakers. We would want to then do, let me clear this. This is where we're going to take the probability of the sample space, 9%, okay, because 9% is the entire sample spaces. That is the division of the entire sample space that this 20 to 24 is, times the probability of owning 5 sneakers or more, given that it's between 20 and 25. So this number on the top would meet the second condition up here. The number on the bottom would be the first condition. So we take times 0.26, and what we find out is that it's actually 2.3%, 2.34% of the entire population are people that meet two conditions. They're between 20 and 24, and they own 5%. Sorry, they own 5 or more sneakers. I hope that makes sense. So that's just for this category. So what we're going to do is we're going to do that for each of these. What is the total population of people between 25 and 34 that are both that age range? Sorry, what is the total? I got to make sure I say this right. What is the total population of people that are first between 25 and 34, and they own at least 5 pairs of sneakers? Okay, so it's kind of important that I say that, right? I'm sorry, I'm misspeaking, but because if I say what is the total population of people between 25 and 34, well, then I'm changing the condition that I'm looking at, because I'm limiting it to 25 to 34, okay? But what I actually want to know is what's the percent of total population that are both between 25 and 34 and own at least 5 pairs of sneakers. So again, we're going to multiply the 0.18 times 0.2, and 3.6% of all people, make sure I say this right, 6.3% of all people are both between 25 and 34 and own 5 pairs of sneakers. Okay? And then we can add these two together. Okay? Then we could add these two numbers together. And what we have then is both of these together. Well, that would be the percentage of everybody, the whole entire population, that's now between 20 and 34 and own 2 pairs of sneakers. Whew. Okay, so anyway, you can see how that works. And then eventually we're going to have to add them all up. But rather than going through that verbally, let me just show you the work. So to break this down mathematically, we want the intersection of A and G, the intersection of A and G1, the intersection of A and G2, the intersection of A and G3, the intersection of A and G4, and the intersection of A and G5. Okay? Which would be the sum of, so if we're trying to find the probability of A, then it would be the sum of each of these intersections. Okay? Does that make sense? Hopefully. But in order to calculate the intersections themselves, we need to take the probability of the subsection of the sample space times the conditional probability of A given that section. And I just did that for, there's 2 lines of work because it's so long. I just did that for the first 2, that the intersections will be it's going to find the intersection of A, which is not listed here. A is not listed in this chart. But we can find the intersection of A, or we can find A, we can find the intersection of A by multiplying the numbers we are given, which is the portion of the entire sample space, times the conditional probability of that, of A given that sample space. Whew. And I just did the first 2 on my calculator, right? Those numbers match what I did. You continue on, you'll do 0.3% of all adults are between 35 and 49, which it's a larger percentage because it's a larger range, by the way. But And then if 13% of people in this age range wear sneakers, then it would be 0.3 times 0.13 would be the number of people in the entire population that is in this age range and owns 5 sneakers. And so we're going to do that for all of them. We're going to add them all together, which, by the way, would have been 3.9%. We do it for 4 and 5. We add them together, and we get 0.1686, which would round to about 17% of all people own at least 5 pairs of sneakers. Whew, that's a lot of writing here, but hopefully it makes sense what each part of that means. So just to be clear, why we're doing it, why we were taking something simple and making it messy is because in this situation we were given the numbers that we can find, that we can plug into the messy side to find the simple side. So yeah, like earlier I was saying, why would you make this messy? Well, it's because we're going to be given this stuff on this side and be able to find the stuff on the left side. So hopefully that makes sense, that how that works. Whew. Gonna have to send me questions if you have any. Kind of feel like there might be some questions. But Bayes' rule, that's what this section is about, Bayes' rule. And the thing about Bayes' rule is that it's a conditional probability it's actually a very powerful conditional probability. I'm going to actually just jump down here to the simpler side of it, because this can look a little messy with the sum and the total probability, but in general, the Bayes' rule, if you have the probability of A given B, you can write that as the probability of B given A times the probability of A over the probability of B. Okay, so why is this powerful? Well, because sometimes we might be given probability, like the given statement here is reliant on us knowing probability of A given B. Well, maybe we don't know the probability of A given B, but we know the probability of B given A. Well, we can rewrite it. We can figure out what probability of A given B is if we know probability of B given A, as long as we know the probability of A and B. And so we can switch it around. I have a video here. Can I play this and will this work? Let me see here. I didn't consider this before I set this up. I do believe that the one issue with playing this video is the sound on the computer. Let's see if I turn that on.
We're going to see in this video, we're going to see an incredibly powerful theorem in the context of probability called Bayes' theorem. And Bayes' theorem provides the basis for something called Bayesian inference, and is a really enormous deal that really changed how we think about probabilities and a lot of statistics in general. Now, I'm going to, in this video, just illustrate the very simplest example, and in the next video, we're going to jump it up to the sort of next level of difficulty. So the first thing I want to introduce is what actually is the theorem. Now, we have seen conditional probability already, so I'm going to remind you that previously we'd seen the following fact. That is, we'd seen that the probability of A given B was the probability that A and B occurred, the intersection, divided out by the probability of B. Now, I'm going to rearrange this. I'm going to go the other way around. So if I have this, I can also therefore look at what happens if I take the probability of B given A. So the same thing, but just flip the other way around. And by comparing these two, it just has to be the probability. Now it's B intersect A. Note that that doesn't matter. A intersect B and B intersect A. I can flip those around. It doesn't make any difference. And then now it's all divided out by the probability of A. So we have these two different components, and you'll notice that there's this portion, the numerator, that these two things are indeed going to be equal. So I can take the one, the bottom one, and I can substitute it into the top one. And so what that's going to give me is that the probability of A given B is equal to, well, the probability of the intersection, but I'm going to rewrite that as the probability of B given A multiplied by the probability of A, and then all divided out by the probability of B, as I have down in the bottom right here. So what I want you to note about this formula, this is going to be Bayes' theorem right here. This is what it is, at least in the single case where we've only got one B that we're interested in. And what we have here is that we can sort of alternate the A given B or B given A. We can change that rule around by multiplying by this particular ratio, the probability of A divided by the probability of B. Now, the reason why this is so helpful is that sometimes computing the probability of A given B is easy, and sometimes the probability of B given A is easy. Sometimes they're both easy, but in any scenario where one of those two is easy to compute, maybe you can go out in the real world and collect some data and figure it out, but that the other of the two is a little bit more challenging, you can use this formula to convert them. You can get from the one conditional probability to the other conditional probability. They're related by Bayes' theorem. So let's look at an example we've seen before in the previous video, but we're going to investigate it in the context of this Bayes' theorem. So the example was if you have a couple and they've got two different children, and you're asserted that at least one of those children is going to be a girl, then what's the probability that both of the children are going to be a girl? So let's plug this into the formula. So I'm asking, in effect, I want to know what is the probability of the two girls, given that we're going to have at least one girl. Well, then this by the theorem tells me that this is the probability, and I'm going to abbreviate even more and just go all the way down to one girl. I mean at least one girl, but I'll just write 1g. Given that I have two girls, multiplied by P of A here. P of A is the first thing, so multiplied by the probability of two girls. And then finally divided out by the probability of B. So this is the probability of at least one girl, which I've abbreviated to be the probability of 1g. All right, so we have this computation. So how can we actually go and evaluate it now? Well, let's look at this conditional probability. The probability of having one girl, at least one girl, given that you know that there's two girls. But if you're being told that there's two girls, then the probability of having at least one girl is 100%. If you have two girls, you have at least one of them. So the P of 1g given the 2g is really, really easy to compute. It's 100%, or it's just the value of 1. I don't have to do anything. Okay, well, that was nice. What about the probability of there being two girls? Well, you might remember that the four cases are, you could have a girl-girl, you could have a girl-boy, you could have a boy-girl, and you could have a boy-boy. There were sort of four different sort of possibilities. But then, if we're going to investigate this, we want to investigate what's the probability of having two girls. Well, there's only one of those four possibilities, so this is just going to be the value of a quarter. And then I need to divide out by the probability of at least one girl. Well, this one has a girl in it, that one has a girl in it, that one. There's three of them that have a girl, so 3/4. In other words, we get 1/3, which is the same value that we computed just by pure conditional probability, but we verified that it works using Bayes' theorem. That illustrates at least some motivation that Bayes' theorem is likely going to be true and useful, presumably, in other contexts beyond this.
All right, so there's that video. Watching the YouTube video and a YouTube video. Hopefully YouTube doesn't have any issue with that and block this video. So hopefully that clarified where this came from. The probability of A given B is equal to the probability of B given A times A over probability of B. And of course you can flip that, but you have to always divide by the second thing here. Put the first thing up here and the second thing down here. First thing listed here, second thing down here. Hopefully that helped. So find the probability that a person, we're going back to the previous example, find the probability that the person selected was over 65 years of age, given that the person owned at least 5 pairs of sneakers, okay? So we already know that we already found that P of A is 0.01686. We found that from example 1. What they are asking here, you have to be careful. They say find the probability that the person selected was over 65 given that they owned at least 5 pairs of sneakers. So the given is 5 pairs of sneakers. That is A, probability of A. And we want to find what's the probability of G5 given A. G5 given A. Okay? So we can find the probability of G5 given A if we use Bayes' theorem and find the probability of A given G5 times the probability of G5 over the probability of A. Okay? So you got to keep in mind what we're looking for. So instead of what might, what was I going to say here? Well, what we're looking for is we are taking everybody that owns sneakers, and we want to find the probability that what is the probability that the person we picked out is over 65. Okay, that's what this is saying here. Okay, what this says up here, this probability of A given G5, is what is the probability that out of the people that are over 65 that the person we pick out owns at least 5 pairs of sneakers. Well, this actually we did already. The A given G5. We did that up here in this other problem. That was part of this problem. A given G5. 1.4. It is this number right here. Okay? So actually we didn't do anything. We just got it. So we know that that is this whole top is what we did already, because this actually will match the last part right here, right? We're multiplying P of G5 times A given G5. So that times the 0.18 times 0.14, which was 0.0252, is actually the top, right? That's what we're doing. It's in a different order, but multiplication is commutative. So the probability of A given G5 will be 14. Okay, 0.14. The probability of G5 is 0.18. Multiply those together. So what we need to do is take 0.20252 divided by 0.16, and we get 0.14. Oh, sorry, 0.01495. Just see something real quick here. 0.0252. Oops. Turn the calculator on. Yeah, I did. Something is off there. I know what I think I know what the problem is. Yeah, it should be 0.1686. I thought something looked weird. I put 0.01, but we know from the last example that that's 0.1686. I was looking at that and I was like, that doesn't look right. Okay, so I'm just going to delete the 0, see if I can move this. Well, actually, let me try moving the numbers over. So I think that the final answer is actually okay. Let me just double check that though. 0.02. I think I probably typed it in my calculator correct. It's just I wrote it up a little wrong. And it should be, oh no, I did write it. So it should be 14.9%, 15%. That does make a little 0.149 is, I think, way too small of a value. But this is from the textbook. Let me just check. Are you kidding me? Okay, there it is. Looking at the wrong example. Thought it was completely wrong. All right, so let me just delete. So yeah, it should just be. I just added some stray zeros in there. So it should be 14.95% or rounding up to 15%. So that's a 15%. Sorry about that. That's a 15% chance that, given the person already owns 5 pairs of sneakers and you select them, it's a 15% chance that they are older than 65. Whew. Again, please send me questions because this is kind of hard to do without you guys here to get some feedback from you as I'm going through this. It's complicated stuff, and it's also the last section for this chapter. So hopefully some of this made sense, and you can rewatch it and also send me questions. Thank you, and good day.